In the second video for this chapter, we will talk about the initial rate method to find the rate law for a reaction and the orders using this initial concentration. So initial rate method just uses the initial concentrations of different reactants. So let's work on slide 36. The question is saying that the decomposition of N2O5, we had it before, and it changes to 2 molecules of nitrogen and 5 molecules of oxygen. We normally set more than one experiment. We need to. And let me show the initial concentration of N2O5 in molar concentration with a 0 sign. So for experiment 1, the initial concentration of N2O5 is 1 times 10 to negative 2 molar. And in experiment 2, its concentration is doubled, 2 times 10 to negative 2 molar. The initial rate of decomposition of N2O5, the rate is 4.8 times 10 to negative 6 molar per second. Remember I told you the rate is molar per second. And by doubling, we have the reaction rate doubled also. We are supposed to find the rate of the order of reaction for N2O5. This is the simplest type of question you can have, just one reactant and 2 sets of experiments. What you need to do, I mean, even before doing any calculations, you can see that by doubling the concentration from experiment 1 to 2, doubling the concentration will double the rate of the reaction. But if you need to write the rate equations, let's write it first. Rate for equation, I call it rate 1. For experiment 1 is K times N2O5. 0. Right? For equation 1, for experiment 1. And rate 2, okay, let me just write there. Rate for experiment 2 is constant, doesn't change, okay? So N2O5, the concentration of N2O5, the initial concentration for experiment 2. Now, let's relate these two, rate 1 over rate 2. All right? You always have to relate the rates. So K and K are canceled. What is the rate 1? Rate 1 is 4.8 times 10 to negative 6 molar per second. What is rate 2 from the table? 9.6 times 10 to negative 6 molar per second. Don't forget that we have M, right? We are going to find M. So because M is the same, let me use it this way. So what is the initial concentration of N2O5 for experiment 1? It's 1 times 10 to negative 2 molar. Because the exponents are the same, we can use it as one fraction. For experiment 2 is 2 times 10 to negative 2 molar. So here is 1 over 2, here to the M, and on the left side you have 1 over 2. So what is M is 1 over 2 to the power of M is 1 over 2, so M is 1. Let's work on little bit more complicated question, which has a different equation and different sets of experiments. Here's the equation. We're working on slide number 38. 2NO plus O2 2NO2, and now you have three sets of experiments. Experiment 1, 2, and 3, and you have the initial concentration of NO, initial concentration of O2. They're all in molarity, moles per liter, and you have the initial rates. Molar per second. So you have 0.0125, 0.0253, and the rate is 0.0281. You have 0.0250, 0.0253, and the reaction rate is 0.112, 0.0125 again, 0.0506, and you have 0.0561. So these are the three sets of the experiments have been done. The initial concentrations have been measured, and now you need to find out the M and N. If you write the rate equation, rate law, it's NO to the power of M. Be careful, again, these are not the coefficients that you see. You need to determine them. They're not given. So let's find M and N. In order to find M is for NO. You need to keep the concentration of, you need to pick, let's say, you need to pick the two experiments in which concentration of oxygen is constant. Because for an equation, for one equation, you cannot have two unknowns. You must have one unknown. So you need to keep this concentration constant to be able to find the concentration for NO. So in order to find M, in which two experiments you see concentration of oxygen remain the same but for NO changes? See it for 1 and 2. You see the concentration of oxygen didn't change but for NO changed. So let's consider 1 and 2. Rate of experiment 2 over rate of experiment 1 will be K. Rate of experiment 2 is NO0 for M and O2 N for experiment 2. And for experiment 1, you have NO2 1 to the power of M and for O2 the same. So now relate them. K and K are cancelled. The rate of experiment 2 is 0.112 over 0.0281. For NO2 is 0.0250 over 0.0125. Again, the exponents are the same, so you can write it as one fraction. Then you can write it as for NO, you will write it as for O2. The second experiment, 0.0253, 0.0253 N. All right, so you can, it's N and N, it's all the same, N and N. So can I cancel them? Yep, I can. So if you calculate the whole thing, then on this side you have 4, on this side you have 2. So what should be M? 2 to the power of what number becomes 4? 2. So far M is 2. So we don't have enough space. Let's clean this part and do the same thing for finding N. For finding N, you need to keep this concentration constant and pick the concentrations that are changing between the two experiments. Which one would you say? I would say 1 and 3. Because the concentration of NO is constant, but concentration of O2 changes. So for N, let's go with 1 and 3. Rate of 3 over rate 1, K, concentration of NO in 3, power of M, and you can do it for O2, power of N, NO, experiment 3, experiment 1, and O2 is. So let's plug in the rate of experiment 3. 0.0561 over 0.0281 is equal to NO for experiment 3, 0.0125 to the second, because we found M as 2, right? And 0.0125, so we can cancel this 2. For oxygen, 0.0506 to the power of N divided by 0.0253 power of N. Now if you calculate, the left side is going to be 2 and it's going to be 2 to the power of N. What is N if we want to have 2? N is 1. Now you can write your rate law as K NO2. And if you pay attention, it's a coincidence that this 2 is the same 2 and 1 is 1. It doesn't necessarily happen all the time. Okay, if in this question you're supposed to find K, you will find it, or let's say you can find it after you find M and N. So that's how you find K, after you find it, because you need to know the rate law. Let's pick any of them. The K must be similar for all of them. So let's choose experiment 1. What is the rate for experiment 1? 0.0281 molar per second. K. What is the value for NO in the first experiment? 0.0125. What is M? Now we have it to the second. And we have O2 for the first one is 0.0253. What is N? 1, that you can skip writing. So K is equal to, after you calculate it, 7.11 times 10 to the third, and it would be per molar square second. Why? Because this is molar per second, and here you have molar square times molar, so you have molar cube. Molar. So in order to find the correct unit for K, you have molar per second divided by molar cube. So you have per molar square second. All right, so here was an example. You have another example on slide number 44, which includes 6 experiments. I'm not going to work on it. It takes a very long time, but the procedure is the same, and you just have more to calculate. One more thing I would like to mention here is for a zeroth order reaction. When you have a zeroth order reaction, if you have A changing to B, for a zeroth order reaction, rate law is just K. Means, you remember, when A is to the power of 0, it becomes 1, right? So it's just K. What was the unit for rate? Is the change in concentration over change over time. So it's molar per second. So for a zeroth order reaction, the unit for K is molar per second. You don't have to memorize them. You just can find it from the experiment. From the formula, sorry. For a first order reaction, let's say you have A again, and the rate law is written as K times A. That's the first order, right? So you have molar per second, and here you have molar. So K is rate over concentration, right? What was the unit for rate? Molar per second. And the unit for A is molar. So molar and molar cancel. So it's 1 over second, or second inverse. So K for first order reaction. Let me show them with 0 and 1. So it's going to be per second, or you show it as per second. All right. And for a second order reaction, let's say you have again, or you can have 2 different reactants and just follow the same format. Let's say you have K A squared. Molar per second again is the unit, and here you have molar square, right? So K is going to be rate over A squared, which is molar per second over molar squared. So one of these, the whole thing, so it's going to be per molar second. So for a second order reaction, you have 1 per molar second, or if you change this molar in mole per liter, then you have liter per mole second, depends on what is given to you. So this is good to know, because you may have a question of determining the unit for K. Okay, in the next video we will talk about the second method of finding the rate law, which is called integrated rate law.